All right, in this video, we're going to be talking about how to convert from hexadecimal to binary. And we're going to do a little bit of binary to decimal conversion as well just to check our answers. So before we get started, hexadecimal, why is it useful and why do we need to learn about it? So hexadecimal is used extensively in computer programming and digital systems because it provides a compact way to represent binary numbers. As we will see, the way of representing a hexadecimal number makes it way more readable than a large binary number. Since one hexadecimal digit corresponds to exactly 4 binary bits, it's much easier for us humans to read and write large binary numbers by converting them into hexadecimal format. And hexadecimal is also used in color codes for web development, where colors are represented as a combination of red, green, and blue, RGB, intensities, each written in hexadecimal. And also in digital circuits and microcontrollers, hexadecimal simplifies debugging and analysis of binary data because long strings of binary digits are hard to manage. And hexadecimal also appears in networking such as IP addresses and IPv6 and MAC addresses, where hexadecimal notation is used for efficiency. So that's just a little bit of an overview. If that's something that you guys are currently taking, you'll see the relevance and you'll see why this is something that is important. So first of all, let's just jump right into it. We'll do a few examples, and I think examples help to really cement the idea in your brain. So we can start with a number like A9, okay? If you're already a little bit familiar with hexadecimal numbers, you've seen this format before, but before we do that, let me just explain that hexadecimal is a base 16 number, okay? So hexadecimal is a base 16 number, right? So you have digits from 0 to 9, 0, 1, 2, to 9, and then you have A, B, C, D, E, I'll put it in caps actually, and F. Okay, so you have 16 digits that you're using. You have 16 ways of representing data. Okay, and every single time that we write a hexadecimal number, it's going to carry a weight of 16 to the power of the position where it's at. Similar to how a number in base 10, let's say it's 157, this would be represented by 10 to the 0. It's like the ones position. This is 10 to the 1, the tens. This is 10 to the 2, the hundreds. Similarly, a hexadecimal number, okay, is represented similarly, where it's 16 starting from 0 and just moving up to 1, 2, 3, 4, and so on and so forth. So if we continue with our example with A9, what we're going to do is we're going to break this into 2 parts, where each, like I mentioned previously, represents 4 binary digits, okay? So if you're already familiar with binary, you know that this is going to be the following. I'm just going to write the weights up here for those that are unfamiliar, okay? And this is just 1, 2, 4, 8. I just rewrote this in expanded form, where it's just the number itself without the powers. So 9 fits into 8, and 1, 0, 0, 1. So this is 9, okay? So 9 is written as this in binary. And then if we take A corresponds to a decimal value of 10, and then B corresponds to 11, C corresponds to 12, all the way up to F, which is 15, which is the largest value that we can represent with 4 binary digits, since with 4 binary digits, you have 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 4. Let's say they're all ones, right? So you're adding all of those up, you're going to get 15, okay? Because you're going to get 8 plus 4 plus 2 plus 1. This is 12, 14, and then 14 plus 1, 15, okay? So if we look at A, which is represented by 10 in decimal, we want to look at the following. So you want to make this a binary number. So 8421, this is our structure and our weights for a binary number. You start fitting it in, you get 1, 0, 1, 0. So this is our representation for A, okay? So combining this together, as we've said A9, we've said that 9 corresponds to 1, 0, 0, 1. And we've said that A corresponds to 10 in decimal, and which looks like the following in binary. And then all we do is we bring these together in the order they are placed in the numbers. So since A comes first, you put 1, 0, 1, 0, 1, 0, 0, 1. Okay, so this is it. This is the hexadecimal number in binary. And a way to check this is, once again, you just do the usual, where we have our weights for the binary number. So it's 1, 2, 4, 8, 16, 32, 64, and 128, right? And then you add. So you have 1 plus 8 plus 32 plus 128, right? Because that's the only spots where we have a 1. So you get 1 plus 8 plus 32 plus 128, which is 169. Okay? And a way to check that is if we just look at A9, this is 16 to the 0, and this is 16 to the 1, correct? So similarly to how we converted binary to decimal, decimal to binary, all you would do would be A times 16 to the 1, which is the same as 10 to 16 to the 1, okay? Plus 9 times 16 to the 0, okay? And this is 10 times 16, which is 160. And this is 9 times 1, which is just 9. And 160 plus 9 is equal to 169. And as you can see, these two values match. So this is a small check that you can do to check that your answer is correct. So we've converted from hexadecimal from right here to our binary representation to our decimal representation, and then we converted straight from the hexadecimal representation straight to decimal without having to go through binary. So you don't have to go through binary to convert to decimal. It's just a step that I did to go ahead and check. So whatever you want, if you're trying to go from hexadecimal straight to binary, you can. If you're trying to go from hexadecimal straight to decimal, you also can. So I'm just going to go ahead and do one more example with a little bit of a larger number, and then we'll wrap up. So I'm going to go ahead and do, let's say, the following number where it is F8AB. Okay, so quite a large number. So as we said previously, you're just going to want to break it up into each piece. So F, 8, A, and B. Okay, so in decimal, what are these values, right? We know F is 15. We know this is just going to be 8. This is 10, and this is 11. Okay, and then we just want to convert these to binary, and then we want to put it all together. So this is going to be 1, 1, 1, 1, because I'll put the weights up here for all of them. This is 1, 2, 4, 8. 8 plus 4 plus 2 plus 1 is 15. And then 8 is just going to be 1, 0, 0, 0. 10 is going to be 1, 0, 1, 0. And then 11 is going to be 1, 0, 1, 1. Okay? And then you just want to put all of this together. Just you want to bring it all together and write it in the order that the hexadecimal number is represented. So you're just going to put 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, and 1, 0, 1, 1. And that right there is your binary representation of the number. And if we go ahead and check what this number adds up to, you can do it straight from hexadecimal. You can do the following. I'm not going to do the binary to decimal. It's going to be a little too large, but in hexadecimal, you have the following. So you have 15 times 16 to the 3 plus 8 times 16 to the 2 plus 10 times 16 to the 1 plus 11 times 16 to the 0. Okay. And if we add that up, we get 15 times 16 to the 3. This is actually a huge number. So this is going to be 61,440 plus 8 times 16 to the 2, which is 2,048, plus 10 times 16 to the 1, which is 160, and then plus 11 times 16 to the 0, which is just 11. And if we bring all this together, we see that 61,440 plus 2,048 plus 160 plus 11 is equal to 63,659. So now you can see why hexadecimal is so useful, because we have represented a number so large. And in binary, right here, also very long and large, you're going to have to write all the weights where it's like 2 to the 0, 2 to the 1, and then do all that. You're going to have to go all the way up to 2 to the very large number over here. Instead, we get to represent it as a very small 4-letter word, I guess you could call it, in F8AB. So that is hexadecimal to binary, and I guess also binary to decimal, and hexadecimal to decimal for you. And that concludes.